What we also can use for relative dating are volcanic markers. When volcanoes erupt, they emit a large amount of ash. The ash will then go in the atmosphere, but since it is melted rock and from the minerals, they have specific compositions. And usually most of the major ashfall from a volcano falls over the next few weeks. So sometimes we see near eruptions and where the ashfall happened, we see an astro-specific volcanic ash layer. So if I have, let's say around Mount St. Helens, in Washington State, you'd have a layer of volcanic rock. In case this picture, it's a very light white layer. If I see that same layer of ash in, say, South Dakota, I know those rocks were about the same time because that specific ash layer, which might only be a few inches thick, all came from the same volcano. So volcanic ash is great for finding the relative time of areas because it covers a widespread area, but over a very small, short, specific amount of time. Now, correlation and relative dating doesn't always work because sometimes there's a gap in the rock record because there's time missing. And there's two ways that we can expect time to be missing from the rock record. And these gaps are due to erosion. So, in the case of New York history, well, we had our glaciers that passed over our rocks. So, as the glaciers advanced, they destroyed layers of rock from entire geologic periods. Also, be a lack of deposition. Since most deposition happens underwater, at the times that New York State is above water, there is no deposition, so there's gaps in that time. So we look at our rock record of New York State or of anywhere, we can see that there are more than one gaps. And if you look at page 8 in your reference table, since this is what we're using for this unit, you'll see that there's no rock or soil from the following periods: the Permian, Paleogene, and Neogene periods. On the very right side of page 8, you'll notice on the top, which is on this inset, it says New York State rock record. For the purpose of this class, both sediment and bedrock are considered part of our rock record. So just in the newest era, only our current period has any rock record, and if you look down here, so here is our current period, there's some rock record, but there is nothing in this column down here, therefore there's been no rock record for these periods. These gaps are called unconformities. This is the general name that is used for all these types. So while going to more specifics, just use the word unconformity for them all and you will be correct for all these circumstances. So an unconformity is a buried surface of erosion that separates two different rock masses, and they represent a gap in geologic time. This just means that while time existed, there's no actual record of it. And on all the pictures that you will see on homeworks, on labs, on tests, usually indicated by a wavy line on the image. Examples that I show you, you'll see how it's pretty obvious that it is a wavy line. Now these separate two separate rock layers. If it's just on the surface, it's just a surface of erosion. So an unconformity is special because it's buried, it's underground. So unconformities are underground. Now the first specific type of unconformity is an angular unconformity. This is when the beds of the flat bedrock are at different angles than the bed above it. These beds have been altered usually to various types of plate tectonics. These are probably the easiest ones to tell because it's fairly obvious that they do not match each other. A nonconformity is when we have horizontal sedimentary rocks on top of non-sedimentary rocks. So we might have some shale and limestone on top of a granite intrusion. And because they're not deposited at the same time, they don't match up. The last type is a disconformity, when we have some horizontal layers on top of other ones, but we know they don't match because they're different rock types. So the pictures below show that the first one, the disconformity, we have limestone on top of sandstone, which would not be formed at the same time. The middle one, the angular unconformity, as I said, you can tell that those rocks don't match up with the layers above it. A nonconformity, that's a granite intrusion that you can tell doesn't match the rest. All of these rock layers, the symbols there, match the symbols in your reference table. We'll give you them sometimes, but you have to know what limestone or sandstone or shale looks like. But once again, notice the wavy line. That is the unconformity. So when you do any work, usually they will not use these specific names, but if you're writing on the lab or an assignment, as long as you write down the word unconformity, you will be correct. This here is a picture of the Grand Canyon, looking at the rock layers. The Colorado River is what has cut through all these rock layers, creating the Grand Canyon. On the right side, we have our different geologic periods. Our Precambrian, Cambrian, Devonian, Mississippian, Pennsylvania, and Permian. We'll look at later about how those should be in order, but they're not all in the order. So if you look at the rock sequence, we have our granite and our schist, our igneous and metamorphic rocks. We have our first nonconformity because this rock doesn't match up with the rocks above it. Highlighted in this green area, purple area. The Unger group, well, this should, see, it's all flat layers, but they're tilted. So they match below, but also doesn't match the sandstone above. So then we have our next unconformity, which are now green. There we go. As we look above, we have more flat sedimentary bedrocks, but these two limestones do not match up because they're from different time periods. So again, this red line here is another unconformity. At the top of the red wall limestone is another disconformity. And as you go up, notice that the time periods go in order. So this sequencing is what you're going to have to do. But if you remember, the bottom is always the oldest. Even if you put one thing out of place, the rest should be fairly simple of how to figure out. Just know that if you think you're missing a step, look at unconformities, or tilting, or faulting, or some kind of event that made it no longer flat and continuous. One thing you do have to know is the steps of how unconformities are formed. So there are 6 steps followed by pictures. So these go along with the pictures that are on the next few slides. So step 1. Sediments are deposited as horizontal layers in a body of water, in a lake, in a sea, or an ocean. Then, in step 2, the lower sediments were uplifted. They were raised above water, and they could be then leveled or tilted during a tectonic event. So now there's no more deposition, so now they're above sea level. Once they're above sea level, they're exposed. And once they're exposed, then we get streams or other erosional forces, wind, glaciers, which then carve surface into tilted beds or into the beds itself. So once it gets uplifted, then weathering and erosion happens. So at the end of step 3, now we have our layers of rocks exposed to the surface of the earth. Then, since an unconformity is a buried gap in time, we have to have more deposition on top of it. So then that land surface will subside, or the water level rises. Either the land sinks, or we get, let's say, sea level rise, which then submerges the erosional surface. So now it's covered with water again. And then once it's buried with water, we get step 5. We get a new set of sediments deposited in horizontal layers on that erosion surface. And since this is geologic time, and this process can take thousands to even millions of years, a lot of rock, we're talking miles at some cases, can be destroyed by the previous erosion. So now we have new flat layers on top of much older layers. And then step 6, the repeat process again. The sequence is uplifted again, it's raised, and exposed to erosion again. And in the case of just having one unconformity, we have the outcrops we see today. This process can be repeated many times. So this is why we see multiple unconformities in some areas. So in the case of New York State, which has a few unconformities, we were once underwater, we were brought up above sea level, but then an ocean formed again over our state, we get more deposition, and then we're back to where we are today. So these images go with the previous 2 slides. So step 1, we have an ocean. You see on the right side, we have our delta coming from a meander, which causes deposition of those flat layers. Then step 2, because of, in this case, continental collisions, we get folding of the rocks, which pushes it above sea level. Now with step 3, that folded layers of rock, well, then glaciers came by, or rivers, or just water in general, and has eroded those curved mountains into valleys and gaps in various landscapes. Then, at the time that it sunk again, and notice the unconformity on step 4 to 5, that black layer. So it's been brought underground, and now the water is adding more sediment on top of it. So these are the steps in order. The top left is our normal deposition. It gets uplifted, and in this case we had intrusion that cuts through all the layers. Then over here we now have our tilted of the rocks. So this has been tilted. It's still underground, but then to the right, it's now been brought under sea level again. So after all this erosion, we got our unconformity, we got our flat layers again over here. And then in the top right, it's been brought above sea level again. And now we have new erosional surfaces on top. So this is how we know things are formed because we know the intrusion has cut through all the layers except for the top one. So the unconforming erosion had to happen after the intrusion, but before the new layers are put down.